Hello everybody. In this video we are going to be looking at the solutions to the college prep magnetism homework problems 16 through 20. Let's take a look at problem 16. We have a wire that is 25 centimeters long, is at right angles with a 0.30 Tesla uniform magnetic field. The current through the wire is 6.0 amps, and what is the magnitude of the force on the wire? So we are given the length of the wire, which is 25 centimeters, which I know I need to convert to meters. So 25 centimeters is going to equal 0.25 meters. Given the strength of the magnetic field at 0.30 Tesla, and I am given the current going through the wire at 6.0 amps, and they want us to find the magnitude of the force on the wire. So if I have the length of the wire, the magnetic field, and the current, looking for the force, I'm going to want to use F equals ILB. Don't need to rearrange everything. I'm already solved for F, so I simply need to plug in my known values into the equation, multiply them together, and I should get a force of 0.45 newtons. Problem 17. A wire that is 625 meters long is perpendicular to a 0.40 Tesla magnetic field. A 1.8 Newton force acts on the wire. What current is in the wire in milliamps? So we are given the length of the wire at 625 meters. We are given the strength of the magnetic field at 0.40 Tesla, and we are given the force that is acting on the wire, which is 1.8 newtons. And we are being asked to find the current going through the wire, but we're also being asked to find the current in milliamps. So when we solve this problem for current, we're going to get a current that is going to be in amps. At the end, we just need to convert from amps to milliamps. So let's take a look and see what we need. We have the length of the wire, the magnitude of the magnetic field, and the force. If we're looking for the current, we want to use F equals ILB. I want to solve that for current, so I'm going to have I is equal to F divided by L times B. I put everything into my formula, and I'm going to end up with a current of 0.0072 amps. And in order to convert from amps to milliamps, I need to move my decimal place 3 spaces to the right, and that is going to give me 7.2 milliamps. Problem 18. The force acting on a wire that is at right angles to a 0.80 Tesla magnetic field is 3.6 newtons. The current in the wire is 7.5 amps. How long is the wire in centimeters? We are given the magnetic field, which is 0.80 Tesla. We are given the force, which is 3.6 newtons, and the current at 7.5 amps. They want to know how long is the wire, but we want to find the length in centimeters. So as with the previous problem, we're going to solve this particular problem for length. When we do that, we'll be given the length in meters, and then we just simply need to convert from meters to centimeters. So to solve this problem, once again, we need to use F equals ILB. Solving this one for length, we're going to have L is going to equal F divided by current times magnetic field. We are going to plug in our known values, and we are going to get a length of 0.60 meters, which when we convert to centimeters, remember to convert to centimeters, I now need to just move my decimal place 2 spaces to the right, and that is going to give me a length of 60 centimeters. 19. A power line carries a 225 amp current from east to west, parallel to the surface of the Earth. What is the magnitude of the force resulting from the Earth's magnetic field acting on each meter of the wire? So in this problem, we are given the current of 225 amps. We're looking for the amount of force acting on each meter. So my length is going to be 1 meter. and we're using the Earth's magnetic field of 5.0 times 10 to the minus fifth Tesla. Now our unknown, what we're being asked to find, is the magnitude of the force on each meter. So my unknown is going to be force per meter. To solve for force per meter, I'm going to want to use F equals ILB, but on my left-hand side of the equation, I'm going to want to have the force divided by the length, F over L. That's going to give me force per meter. So I know that when I plug in my known values, when I plug in my length of 1 meter underneath the force, that's not going to change the value of the force because I'm just dividing by 1. And I need to multiply the current of 225 amps by the magnetic field of 5.0 times 10 to the minus fifth Tesla. And when I do that, I'm going to get a force per meter of 0.011 newtons per meter, which I can also convert to millinewtons per meter, move my decimal place over 3 times, and I'm going to get 11 millinewtons per meter. The next thing that they want us to find is the direction of the force. So if I go back into the problem, I know that my current is running from east to west. So my current is going in this direction. And if you remember from the PowerPoint when we talked about the Earth's magnetic field, we know that the magnetic field runs from the south pole, the south magnetic pole, which is actually a north pole. If you consider the Earth being a large magnet, that's the north pole down on the south or the bottom of the Earth, and the south pole on the top of the Earth. And the magnetic field runs from north to south. So my magnetic field on the Earth is going to be running from the south to the north. So this is my magnetic field. So if I use my right hand rule, and remember for the right hand rules, because I'm doing this in a camera, the camera acts as a mirror, so I'm actually going to use my left hand, but you need to use your right hand because this is a right hand rule. I know that if my current, which are represented by my fingers here, my current is running to the west, so that is to the right, or I'm sorry, to the left in your screen. And the magnetic field is pointing to the north, which is going to be straight up. I need to stand up to do this. Going straight up. Right. My fingers are running to the left. My palm is sticking straight up to the north, and my thumb represents the force, which is going into the screen. So my thumb is going right into the screen. That is going to be in the negative Z direction. Problem 20. A force of 5.78 times 10 to the minus 16th newtons acts on an unknown particle traveling at a 90-degree angle through a magnetic field. If the velocity of the particle is 5.65 times 10 to the fourth meters per second, and the field is 3.20 times 10 to the minus second Tesla, how many elementary charges does the particle carry? Let's take a look and see what we're given in this problem. We are given the force acting on the particle, which is 5.78 times 10 to the minus 16th newtons. We are given the velocity at which the particle is traveling at 5.65 times 10 to the fourth meters per second. And we are given the strength of the magnetic field, 3.20 times 10 to the minus second Tesla. We are being asked to find the number of elementary charges that are contained within the particle. So if I'm dealing with elementary charges, I know that I want to find the charge of the particle. You could also use a process of elimination. I am given the force, the velocity, and the magnetic field. So I know that I'm going to need to use F equals QVB, and the only variable that I don't have in that formula is charge. So just by process of elimination, I know that I'm going to need to solve for charge. When I solve this equation for charge, I get Q equals F divided by VB, or velocity times the magnetic field. I plug in my known values, and I'm going to get a charge for the particle of 3.20 times 10 to the minus 19th coulombs. Now that's the total charge of the particle. I know that one elementary charge, we use the symbol E for elementary charges, is equal to 1.60 times 10 to the minus 19th coulombs. So that becomes my conversion factor to go from the charge to the number of elementary particles, because I know one elementary particle has this charge. So I want to end up with elementary particles. So when I multiply the charge of the particle, which is 3.20 times 10 to the minus 19th coulombs, by this conversion factor, I know I'm going to want to have the elementary particles in the numerator and the charge in the denominator. That way my charges will cancel out and I'll just be left with elementary particles. And when I divide 3.20 times 10 to the minus 19th by 1.60 times 10 to the minus 19th, I'm going to get an answer of 2. So this particle contains 2 elementary charges, or